All right, so there's a few times in I can recall back my first semester in when I was sitting in your seat, my first semester in college when I was in Calculus 1 at university. I can recall, uh, for the most part, probably mirroring paralleling your experience. For the most part, pretty bored through the beginning. But then every once in a while, my ears would perk up, and a topic would be introduced that I, either I found interesting or useful. Like all of a sudden, I could see some value, some utility in what I was learning, and this is one of those topics where I really fell in love with the subject when I was a freshman, and the topic is optimization. So the idea of the optimal, meaning you could think of the maximum or the minimum that you for example you could be asked, what is the maximum that you bench press, or what is the minimum cost? These are what we call optimal values, right? That is the goal. If your goal is to say lower cost, the optimal would be to have zero cost. And we could think about this. There's the optimal. You can think about the optimal distance or voltage or size, or nevertheless, I mean, but we speak in minimums and maximums all the time, and we're always, when we talk to each other, we're always asking each other about what's the maximum or minimum. What's the fastest the car on the market? The maximum speed, or how fast can it go 0 to 60? All of these are just, again, ways of talking about optimal numbers. And the whole point of this section, 3.7, is to discuss optimization. Now, I'm going to start with with no theory, nothing. We're going to jump right in. I'm going to start with just a baby problem, one that you probably don't need calculus to do. Ready? Let me read. So, the product of two positive numbers is 185. Okay? And the sum of those two numbers is a minimum. Interesting. Okay, so clearly we're looking for two numbers, right? I'm just going to make up something. Let's just say x is the first number and y can be the second number. So we are looking for two numbers. Now, the stipulation is they're both positive numbers. And what we're told that whatever these two numbers are, x and y, we know that x multiplied by y is equal to 185. But what we want is the sum to be a minimum. Right? There's a whole lot of numbers that multiply to be 185. But we want the sum, when you add those two numbers, we want that to be a minimum value. This is an optimization type of problem. So I'm going to erase that word min, and I'm going to write something else in just a second. But I want to revisit a theorem back in the early part of chapter 4. This is from 3.4, where we were looking at the second derivative test. Now, just remember that the second derivative test is a way that you can find relative mins and maxes. And the only thing that it requires is that you know where the first derivative is equal to 0. The second derivative has to exist. And then the second derivative is a positive number, right? Does that make sense to you? That if I know if I know where the first derivative equals 0, and I know that the second derivative at that same place is a positive number, then I have a minimum. So, okay. So now let me see if I can address this question. So I'm going to label the x plus y. I don't know what x plus y it actually equals because I don't know x and I don't know y yet. But I know that its sum, I'm going to write s because it's a sum. I know its sum should be a minimum. All right. Now, how do you proceed from here? So your first thought should be, well, I'm in a calculus class. This is a calculus problem, so let me take a derivative. Okay, great. But what are you going to take a derivative of? Well, for right now, you haven't studied multivariable calculus, so you are in single variable calculus. You do know how to implicitly differentiate, but nevertheless, this question still remains, what are you going to take a derivative of? So the way that we're going to do this is, since we actually want to be able to rewrite, right? This is, in other words, stay with me here. There's no calculus being done right now. So I want to be able to rewrite this equation such that I only have one variable, right? I want the other variable to be expressed in terms of either the first or the second variable. So let me see if this makes sense to you. So if x multiplied by y is equal to 185, then that means that, say, y is equal to 185 over x. Do you agree with me? All right, well, that means wherever I see a y variable, I can write that as 185 over x. And that's exactly what I'm about to do. So notice what's going to happen right now, right? So notice that you're going to go from an equation of two variables to an equation of one variable. So this is going to become x plus 185 over x. Now, it's still equal to a sum that I don't know of, but can you appreciate that at this step you can find the sum by only knowing one value, right? And up here, if you ask me what's the sum, I would say, well, first give me the x and the y, then I'll give you the sum. But here, if you ask me what's the sum, you only have to give me the x, right? So, okay, so interesting enough. So now what we're going to do is take a derivative. And again, I offer this first example without any priors, right? Without any background at all. I just want to show you how this could work. So let me rewrite this as s equals x plus 185 over x, right? Just rewriting it because we're used to having the y on the left side. And now if I take my derivative of s with respect to x, let's see what that looks like. Well, the derivative, I'm just going to produce this. Derivative of x is 1. Again, if you would write this as 185 times x to the power of negative 1, and then you can take your derivative, but that's going to end up being minus 185 over x squared. No time to go through things that you should know by now. All right, and now I tell you what, instead of having ds over dx, let's just write, you like y primes and f primes, don't you? I think you do. So I'll just use S prime. Makes our work a little bit cleaner. So, and now S double prime. I'm going to take a second derivative. All right, well, the derivative of 1 is going to zero out. And again, you would take this 185. You can rewrite that as minus 185x to the power of negative 2. That's what a quick way of knocking out the derivative. And when you do, you're going to end up with a positive number, a positive 370 over x cubed. Okay, now none of this has gotten to this, the answer of two numbers that multiply to be 185 that add up to be, or sum to be a minimum. Maybe you've tried it. Did any of you try it on your own without any calculus? Okay, well, so let's actually recall that. Remember the idea of critical numbers. The idea of critical numbers and how they play a role in finding extrema. Well, remember that we're going to, of course, we're going to assume that positive number is greater than 0, right? Obviously, 0, 0 doesn't have multiply to be 185 anyway, but nevertheless, what we're going to do is we're going to take this first derivative and we're going to find it's in critical numbers, but more importantly, we're going to find where it equals 0, right? Because that's going to be important to our problem. So if I take S prime, which is equal to 1 minus 185 over x squared, let's set that equal to 0. So 0 is equal to 1 minus 185 over x squared. Let's go ahead and I'm going to do two steps at once. Okay, I'm going to subtract this 1, so I'll have a minus 1, and I'm going to divide by negative 1 on both sides. Okay, that gets rid of the negative symbols. So that leaves me with positive 1 is equal to positive 185 over x squared. All right, so if I multiply both sides by x squared, I have x squared is equal to 185. And that means x is equal to, now it is equal to plus or minus, but remember it's two positive numbers, so the square root of 185. Okay, so how do I know? Well, so potentially, right? So potentially the x value is the square root of 185. I haven't shown that that's a minimum, but let's just continue. So, will you agree with me that let's go to this equation right here where y, ready? I'm going to box it in for you, where y is equal to 185 over x. So you agree with me that if I know what the x value is, I can get the y value, correct? All right, well, let's actually do that. So in this case, y is going to be equal to 185 divided by, right, because I'm just using this equation, y is going to be equal to 185 divided by what? Divided by the square root of 185. So what is 185 divided by the square root of 185? Well, if you rationalize that denominator, the square root of 185 over the square root of 185, then you end up with, oh, I've ran out of room. Okay, let me see if I can grab this work. No, I'll grab just this part. No, that's not gonna work. Let's see if I can grab this part. So sorry. All right. Since it's the first problem, I'm going to take my time. So y was equal to 185 over the square root of 185, to which I said, go ahead and rationalize. So what does it mean to rationalize? Well, the denominator, we're going to multiply by the square root of 185 over the square root of 185, which is just a nice way of saying, a fancy way of saying, hey, let's just multiply by 1, right? Because that's just equal to 1. So that leaves me with y should be equal to 185 square root times the square root of 185 over, well, what's the square root of 185 times the square root of 185? 185. Well, the 185's cancel, leaving me with the square root of 185. So hold on for a second, hold on. So I potentially have I have an x value of the square root of 185 and a y value of the square root of 185. Now, I haven't shown that if I add those, that's going to be the minimum value. But can I first check that initial condition? If I multiply them, the square root of 185 times the square root of 185, does it multiply? Is the product 185? Well, yes. So now how would you proceed to show that that is a minimum? So how would you proceed to show that if you take the square root of 185 plus the square root of 185, not only does that multiply to be 185, but that adds to be the minimum. There are no other two numbers out there that would multiply to be 185 that would add up to be anything smaller. So how do you do this? Well, remember, the second derivative test said that if let me give myself a little bit of space up here so we can read the theorem. So the second derivative test said that first figure out where your derivative is equal to 0. And we did that, right? We figured out that our derivative is equal to 0 at the square root of 185. And then, okay, assuming all the conditions are met, then plug that value into your second derivative. If you get a positive number, you got a minimum. So the last thing to do is to take our second derivative. Now our second derivative was equal to 370 divided by x cubed. So if I take that value where the derivative was equal to 0 and plug it into my second derivative, what do you get? Well, it's not really a question of what do you get, it's a question of what's the sign. Is it greater than 0 or less than 0 or equal to 0? And in this case, it would be a positive number. It would be concave up. So when you have concavity concave up with a horizontal line representing the slope equal to 0, then what do you have? You have a minimum. Now, that is correct. Those are the solutions. So this first initial problem was everything that we've just did. We're going to continue to follow a recipe. The problem is I didn't lay out the recipe very well for you. We just tackled it using the second derivative test. So where I want to go now is I want to start to show you how you can, because no one really, be honest, you really don't care. You didn't really care what the answer was, did you? Maybe you did. But I want to start to do some problems where you might actually value the solutions, or at least see why somebody would value the solution. And along the way, we need a recipe for how do we tackle these optimization problems. So let me start by reading this question. and then I'm gonna start to give you some steps and more of a recipe, a guideline. Ready? So here it is. A manufacturer wants to design an open box. Now, open box, that means, so here's your box over here, right? But an open box, that means there's no top, right? There's no top to this box. So the manufacturer wants to design an open box having a square base. Okay, so again, I don't like to read word problems all the way through. I like to pause and make sure I understand. So a square base, that's going to mean that for whatever box this is, the length is going to be equal to the width, right? With me so far? Now, okay. Now the manufacturer has a constraint, right? And you think about it, we always have a constraints. So for example, you only have 24 hours in a day. That's a constraint. So that constrains your optimization up to how much you want to, say, produce. Now, in this case, the constraint is the surface area has to be 108 square inches. Now, again, I don't like to just keep going. Does it make sense to you that right now you're staring at a flat piece of cardboard, right? That you're the manufacturer and you just have a flat piece of cardboard. Now, what you're going to do is you're going to fold this up to make a box without a top on it. And you don't care what this box looks like. You don't care the dimensions, none of that bothers you. What you care about is that it has the maximum volume. You want to be able to put as much as you possibly can in this box. But the constraint is important. The surface area is going to be 108 square inches. So now let's see if we can start to piece this together. So if you think about, we'll see how you do here. So if you just have a flat piece of cardboard and you're going to fold it up, well, first you're going to have to cut. Do you agree with me that I'm making if I cut those 4 corners off, I could then fold each flap, right? You could then fold the flaps. And then do you agree with me that the result would look like this box without a top on it? Does that make sense? So you got your scissors out, you're ready to start cutting, but the question is, how much should you cut? That is the dilemma. So now, how do you solve this problem? Because this is going to require some calculus. So the first step in these problems, well, let me go ahead and say, honestly, is to draw a picture if one is not given to you. Right? I know that I am an incredible artist, but even if you're not an incredible artist like myself, you can still no matter how bad the picture looks, sometimes just having a picture to go along with the words can help guide you through the problem. But step 2, and let me be honest, the hardest step, is to find 2 equations or formulas that relate to the problem. All right, now the first formula that comes to mind if you're dealing with a box, well, normally So the volume of any cube here is going to be its length times its width times its height. And I'll just go ahead and say the surface area what I'm going to do is move this here. So that's the volume. The surface area well, instead of trying to find a formula for it, think about it. The surface area. If you have a volume is the question of how much goes in the box. Surface area is the question of how much wrapping paper goes over the box, if you will, right? So the surface area is simply going to be the area of the base plus the area of each wall. Now, do you agree with me that since we don't have to worry about the area of the top because this is an open top box? So, all right, so these are two different formulas that both deal with a cube. And so now let's see if we can actually start to plug in some values. All right, well, let's start with volume. And I'm moving slow only because the setup is the most important. So this is not a good volume formula for us, right? I mean, we know how to take derivatives, but with respect to one variable. Right now I have three variables, lengths, widths, heights. So I don't want this volume formula. But the good news is, since it's a square box, don't you agree with me that the length is just, if you call it x, that's what I'm going to call it, then the width would also have to be x? Makes sense so far, right? So and that means we can write our volume formula as x squared times height. Okay, so now that's a little bit better. That's a little bit better. So let's see, we'll have to see where we can go with that. All right, ready? Let's actually figure out the surface area. So for short, I'm just going to put S dot A surface area. Ready? So what is the area of the base? So do me a favor. So I will try my best to shade in. So if I'm looking at just the base of this box, what's the area? Well, area is always going to be length times width, so that's just x times x. So far so good. So that's x squared plus, now the area of each wall, so you can imagine each wall has its own area. And how many walls are there? Well, there's 4 of them. So this is going to be plus 4 times, okay, what is the area of one of the walls? Ready? Let's do this one wall right here. What is the area of this wall? Well, it's going to be x times h. Okay, now you're on to something. The only thing is that we actually have a little bit more information about that surface area. Don't you agree that we actually know that the surface area must equal 108, right? So I can now write this as 108 is equal to x squared plus 4xh. And now we are done with step 2. So what I'm going to do is I'm actually going to give these equations some names. So not that I'm renaming volume or surface area, but more importantly, more germane to the topic at hand is this volume formula is what we call the primary. This is the primary equation. Now, how do you know which one's primary? Well, the primary equation is the one that you want to optimize, right? Are we trying to optimize the surface area? No. The manufacturer wants to optimize the volume. They want maximum volume of this box. So the primary equation is always the one that you're trying to optimize. The second equation, or the secondary equation, is going to be your constraint. Right? I mean, there has to be some constraint. There is a finite amount of cardboard that this manufacturer has access to, right? So there's some constraints. In this case, the constraint is the surface area has to be 108 square inches. So now, where do we go? So step 3. So step 3, we are always going to substitute before we take any derivatives. All right? Right now we have 2 equations. So the goal of step 3 is to solve, and what I'm about to write next is important, solve the secondary equation right? Solve the secondary equation so that you can plug in the primary equation. Now, if your question was, well, solve it for what, right? Well, that's a good question. That's why I didn't write it there, because it's, here's my secondary equation. 108 is equal to x squared plus 4 times x times h. Now, if you ask me, okay, solve it, but solve for what? Well, it's up to you. You just want to be able to solve for a variable that exists in your primary equation, right? So I could solve for h, I could solve for x. Obviously, the h is going to be a lot easier. It's going to lend itself a little bit more. So I'm going to solve, in this case, I'm going to solve for h. And what do we get? Well, we would get h is equal to 108 minus x squared divided by 4x. Now, I don't mean to drag out the problem. Let me be honest with you, if you're bored right now, it's actually a good sign, because for many, this is one of the hardest topics of calculus. So if you're just anticipating where I'm going, or if you're saying, why does this individual just take so long, just get there? Well, you need to relax, because there could be someone else that is really struggling right now, and I'm talking to that person, not you. Got it? You're not in the conversation. Although, it's a good thing, because that just means you are ahead of the curve. So, we're done with step 3. I'm gonna go to the next page, and but I'm gonna show you what I'm about to do with an arrow for step 4. What I'm gonna do is I'm gonna take this new h and plug it into the primary. Okay? So let me now go to the next page. Oh, well, let me now produce a next page. How's that? So let me see if I can take, well, nope, I'll just rewrite it. So step 4, we are going to substitute the primary equation. Right, we're going to substitute, in this case it was the h. H was equal to 108 minus x squared over 4x. We're actually going to substitute that into the primary equation. Let me go ahead and write the primary equation. So the primary equation was v was equal to x squared times h. Okay, are you ready? So the whole point of that solving, the whole point of step 3 was so that I can substitute that h in for my primary equation. And now I want you to take a look at what we have and appreciate what we have. So 108 minus x squared over 4x. Do you realize that we have done no calculus yet? Right? So let's appreciate what this is. So before, if you wanted to find the volume of this open top box, right? So you got this box over here with no top on it. So before, the volume, I would need a length and a width and a height. But because we had a square base, we were able to figure out that, hey, I can find the volume if you just give me a length and a height. But after substituting, do you realize now all I need to find a volume is just a length? That's pretty amazing. It's just in terms of one variable. So I'm going to go ahead and distribute this equation so that it makes my work for step 5 makes it a little bit easier. So what does v actually equal? V is going to be equal to, so if I distribute this x squared, and I'm going to break up the fraction, so this is, v is going to be equal to 27x minus x cubed over 4. All right, there's my new volume formula. Ready? Let's go to the step 5. So step 5 is when you finally start to use calculus. So you could go through it. Well, I'll tell you what. I'll come back to this. For step 5, we're gonna take the derivative. Trying to be. So we're gonna take the derivative. Of step 4 and set equal to 0. Okay, so what is the derivative? So now I want v prime. Okay, so I'm going to go through this quickly. So the derivative of v with respect to x is going to be, what, that's going to be 27 minus what? Minus 3x squared over 4. So that's my derivative of my new volume formula. And I'm also going to set that equal to 0. 0 is equal to, just trying to give myself enough space. So 0 is equal to 27 minus 3x squared over 4. All right, so that makes sense because the critical numbers, or in our case, the numbers where the derivative is equal to 0 is going to help us find our minimums and maximums, and that's what this manufacturer wants. So now we're just simply going to solve for x. Okay, so if we solve that equation for x, we end up with x is equal to 6 and negative 6. Okay, so x is equal to plus or minus 6, 6 and negative 6. Okay, so I don't know what it means to have a negative 6 length, right? So I'm going to throw this away. Mathematically, it's sound, but doesn't make any sense to our application. Okay, so the last step, did I really just write 5 twice? Did you notice that and start laughing? Were you laughing at me? How dare you laugh at me? Okay, so the last step is going to be to plug in this new x value into our volume formula. So v of 6. After I do this, I will comment on the domain to this as well. But so if you plug in, let's just make sure you follow me here. So you know that x is equal to, so you're going with x is equal to 6, right? That was where we left off with x is equal to 6. We threw away the negative 6 because it didn't make any sense for what we were doing. So if you take that positive 6 and plug it in to your volume formula, does it make sense you want to plug it into the volume formula where you don't have an h, right? So we would plug in to the volume formula that only requires the x value. So that would be 27 multiplied by 6 minus 6 cubed over 4. The result is 108. Okay. Now, let me make sure that you understand the idea that the maximum volume you can get from this open top box, the maximum volume you can get, given that it has to be 108 square inches for surface area, the maximum volume you can get is 108 cubic inches. Okay? Now, the only caveat is, if you recall, that maximums and minimums can exist at critical numbers, which is what we have here, as well as endpoints. So I'm not going to dwell on this step right here, but the domain, there is a domain of v that we did not consider in this problem. But if you don't mind, let me punt on that. Let's rejoice in the fact that we actually found the maximum volume using a little bit of calculus that we all know how to do. And now you turn to this manufacturer and say, I've just ran the numbers. You can get 108 cubic inches of volume from that box. And then the let's say the president, the CEO is so happy. They're like, okay, awesome. So tell me, what dimensions what dimensions of box should we have, right? So in other words, the CUO says length times width times height. Can you please tell me what the length and the width and the height needs to be to make that 108 cubic inches? All right, well, we can do that. So in our case, remember, it was x times x times h. I use dots instead of time symbols. So what are the dimensions? Well, can you agree with me that as of right now, since I know that x is equal to 6, I know this is a 6 by 6 by, hold on, I don't know the height yet. But if you have been following along, don't you agree that you can find the height as long as you know x? I'm going to hold this here for a second. See, that's why we want to keep our work nice, neat, linear, label things. Because now, look, I have this h height formula staring at me. If I plug 6 in for x, it will give me the height. And what is it? That's a 6 by 6 by 3. That is the dimensions of the box that will produce the maximum volume for this box that has this open top box with a surface area of 108 square inches. All right, this is optimization. I will be back soon with some more videos.